Hello, good afternoon, everyone. I'm just going to make a quick recording here. So last time we went over the moment redistribution. What we learned is that if we utilize the formation of plastic hinges, then we can reduce the amount of reinforcement and realize the full moment capacity of the continuous beam. So we did this last time, and like we said, the way it is done for continuous reinforced concrete beams is indirectly. We don't actually do a plastic analysis, but what we do is that wherever your strain and the tension steel is greater than or equal to 0.0075, then you can do moment redistribution there. That is, you can reduce the moment by a percentage equal to either 1000 times epsilon t, that is the strain in the most farthest layer of steel, or 20%, whichever is smaller. So you can use that to reduce the moments. So then, so that your design becomes more economical. So we went over the way that they are doing this, calculations, and we also did one sample calculation. That is, I think we did it for same as them. We did it for negative moment at support D. So I will just go over that briefly. So we said that we have given moment is 49.3 kip-foot there at support D. You can see as per the moment envelope, maximum negative moment is 49.3 kip-foot. So we want to reduce that. So what we do is, okay, they have used some direct formulae, but just a second. We did this from scratch. So for that 49.3 kip-foot, we will determine how much reinforcement is required, what is the corresponding strain in the tension steel. So first, where is the neutral axis? According to that, what is the strain in the tension steel? And then we will take the minimum of 1000 times that strain, or 20%. So either of those can be used. I mean, minimum of those has to be used. Okay. So like he did it here, the strain comes out to 0.0267, and our file is not yet. Okay. Okay. Okay, still not yet open. It's okay. So what we are doing there is just like this. We determine the strain and the tension steel. Then he gets 26.7, but the lower is 20. So you adjust by 20%. That means you reduce the moment at that support by 20%. So now this is your design moment at that support. Then you redo it, then your strain will be even higher, and again your adjustment is same. That means after one iteration, if you're still getting the same adjustment, then this is the adjustment. This is the correct value. If you get a smaller value here, you need to use that smaller value. Okay, so okay, I think we kind of did a quick version here. So we are 49.3 kfoot. So our compression block force is 0.85 C prime AB. That's ASFY. So we need this much. So this times D minus A over 2. And then we have 4,000 PSI concrete. A is 12 inches for the, I'm sorry, B is 12 inches. And then D 14. Let me check the document. I have it here as well. Let me just check there. D. Yeah, D is 14 inch. So doing that, we solved for A, and then we could get 0.003, or epsilon T is 0.03. I think I might have rounded it up. No, it's fine. I think somewhere there is some approximation in what I did. Yeah, otherwise we will get the exact answer. Anyway, it's 0.03 is the strain. So it's either this times 1000, which is 30, or 20. So 20% is the reduction. So as we said, the whole procedure of doing momentary distribution for the design, starting from first determining for each load pattern the moments along the spans at every support, then doing that for every load pattern, then getting the moment envelope. Then once we get the moment envelope, going and doing the momentary distribution at every support, it is manually, it is very, very time consuming. So therefore, in general, the software is used. So now I'm going to show you how we can do this using the software. So we will use the software SP Beam. So I'm using computer in lab 227. So let me exit for now. So what you need to do first, type SP Beam in your search. Start SP Beam. Okay, so there is now no license problem or anything. And here, go to input, data input wizard. Okay, so project, you can say continuous beam moment redistribution. You can say, east, west. Number 3, something. Number of supports. Okay, now we need to give our specific things. So how many supports we have? A, B, C, D, 4. So I'm going to give here 4. And no cantilevers. All of them are supports. Span control. This one is fine. I think this one is XCL, means it's saying not a cantilever. Okay. So, okay, that's fine. In solve option. Okay, so now you can see here it says momentary distribution. You have to check it. And now we can go to next. Concrete is 4000 psi, that's fine for both columns and beams. Modulus and modulus of rupture, that's fine. Steel is 60 ksi, modulus is always same, that's fine. Now span 1. So slabs. So this is a bit tricky in SP, beam, SP slab. Both are same software. We don't have slab here. So what we do is width and thickness, you just give us 0. So what is the span? 25 feet, 15 feet, 20 feet. So go there, give the span 25, say modify. Then this one, span is 15. And none of these things. Because if it is assuming that there is a slab with a beam, now we are saying only beam, no slab. Modify. Then third span, 20 feet. There is nothing. Thickness. First span is exterior left. Modify. Last span is exterior right. Modify. Okay. So beam. Now, if you notice, our beams are all 12 by 16. So 12, 16. Modify. 12, 16. 16. Ribs. We don't have any ribs. Okay. Now columns. So how are the columns? Columns are 16 by 16 at all the supports. So height. So if you notice, story height is 10 feet. So our columns are above 10 feet, below 10 feet. Column is 16, 16, 16, 16. Okay, modify. Then copy. All the columns are same. Check all. Okay. 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 Now column capital. We don't have any capital. So transverse beam we don't have. Momentary distribution. Okay. So this one we are doing, we will just do according to, if you follow the same PDF file, the structure point people, they have done it only for second and third supports. So we will also do only there. So second support, redistribution limit. If you remember, you cannot reduce more than or redistribute more than 20%. Okay, whatever you reduce at the negative moments, after you do the reduction, then you need to recalculate your positive moment, right? So positive moment will increase. All are not decreasing, but negative moments are decreasing. That itself will bring the economy in the design. Negative moments, you did 20% or 1000 times epsilon t, whichever is smaller, you reduce by that much. Now, based on that, your positive moment will go up, but that's okay. You will still get more economical design. So give 2020, modify. Number 3, 2020, modify. Definition of the column. Column is fixed on top, fixed at the bottom. That's fine. Slabs and ribs, beams. That is okay. Then, okay, one caveat here. So in the SP beam, SP slab softwares, the calculation in the document is all done without self-weight. So you just delete this case. Okay. Now these are all from ASC 710, the same load combinations as per LRFD. So no need to check. Now we need to give dead load and live load. How much is the dead load? 1167 pound per foot. Live load 450 pound per foot. Now dead load, line load. Magnitude start 1167 and also 1167. And it is 25 feet. Oh, sorry, add. Okay. For span 2. Still same, but span 2 is only 15 feet. Oops, only span 1. Yeah, span 2 is 15. And this should be span 1. 5. Okay, all of span 1, all of span 2. Now span 3. Span 3 is 20 feet. Okay. Span 3 or entire length of span 3 span. Okay, looks okay. Now live load. Live load is 450 pound per foot. 450, the entire spans 25 feet. Two, span 3, and Just a second, just a second. Okay, span 3 is that much. So we gave all the live load and dead load. Now don't have any give all our rigid supports. We don't specify any moments. We are not doing lateral loads. So finish. Save. So already did. Save. Now this is top view. You can see the plan. You can see all of the views. Okay. Okay. So now I think we have entered everything. So we can go ahead to solve. So we solved it. What we need to, main things we need to check. So I have the document open. I have the document open here. So we will see first what are the loads. Okay, we have to. Now it will do all of the patterning by itself. It will do all the patterning by itself, all of those alternating patterns and everything. So no need to worry about that. Now we check the internal forces. Okay, so now this is the moment diagram. Now this is already redistributed, but we can compare. Go to options and do both redistributed and non-redistributed. Now you can see clearly here. So dotted one is before moment redistribution. So we did in this support and this support. So you can see dotted one, negative moment comes down after redistribution. Of course, positive moment will go up slightly. Okay. And you can see also reinforcement. So here, I think that's the final reinforcement only that it shows. But this you can see moment capacity, okay? So this moment capacity, you can actually, this is our moment capacity using moment redistribution. but you can also uncheck the moment redistribution. Now let's take a snapshot of this. So this is our moment capacity by using redistribution. Now let's go here, general information, remove moment redistribution, save, solve again. Now check the moment capacity. Now let's compare with this one. So you can see that we using the moment distribution. Oops. You can see we were able to considerably get some saving. Okay. See, anyway, the moment envelope is here. So using the moment redistribution, we really were able to reduce the negative reinforcement at these regions. Okay. Okay. So this was all a very short recording. Hopefully you can go. I think I still have to get the remote desktop permission, but if you're on campus, you can just go to lab 227. You can run it, and I will send one assignment now about this. You have a small hand calculation there using the software. Okay, thank you. Have a good day.